Hello, everyone. So we are welcome in, if you've decided to join me. I am just a working class alien looking for, well, watching some cool space stuff today, hopefully. I've been hearing about the announcement that astrophysicists are really happy about. And it was enough... I got enough information about it to know that it would be a cool thing to watch. I'm sure there's a preliminary write-up of whatever they're going to announce today online somewhere, but I didn't get that deep into it. So I figured, you know what, I'll just watch the thing. Like, why not? So I've got the YouTube stream up. It's supposed to start in about a minute. And yeah, we will see what's going on. I am not an avid astrophysics fan. It was something that's sort of like, it's kind of like the background in your life. You know, before I ended up on Earth, when I was still out near my home world, astrophysics is kind of the type of thing where you learn enough to, it's kind of like understanding the weather, you know. You don't want to go out in a hurricane. You want to protect yourself. So same kind of thing, you know. I have a somewhat better knowledge of it than probably the average Earthling, but it really is just more of a functional thing where I come from. And yeah, I am. It's more interesting to me in terms of how, you know, this could impact knowledge progressing for people here on Earth. So I am looking forward to seeing what is going on. When this thing actually starts, I can throw it into full screen, hopefully, because having my own chat, having a chat scrolling on the screen that is not my own chat, it's a little confusing. So, and they haven't even started yet, and it's already moving pretty quickly. So I'm imagining it's going to go ballistic once they actually start broadcasting. But we'll see. It's all, I'm sure, way more information than you all needed. Oh, that reminds me, there's a solar eclipse next year that I gotta remember to put that on my calendar. Again, these are the types of things that you often just don't, you know, where I come from, you pay attention to them to the degree that you pay attention to the weather, you know, just if they're gonna get in your way, which is fine. So I hope everyone out there is doing well today. Where I am in the planet, it is currently Thursday afternoon. And yeah, I'm just, you know, taking a break from work to check this out. And we're going to see what's happening. They're running a little bit late, which is, well, they're not really late. They're all of 1 minute late. I should not be so impatient. But yeah, hopefully you all are doing well wherever you are in the world. I would say, or wherever you are in the galaxy or the universe, but this is not, well, their signal is probably being broadcast over standard broadcast technology. I am not. I am limited to the internet, so nobody off planet's going to hear from me, which is an ongoing concern for me. It's the reason I stayed here after crashing here when I did.
Jackson, Director of the Green Bank Observatory, Dr. Tony Beasley, Director of the National Radio Astronomy Observatory,
we'll put it in theater
and
mode.
Dr. Adam Cohen, Director of Associated Universities, Inc. We had also hoped that Olga Figueroa Miranda, Director of the Arecibo Observatory, would join us today, but I think she had some problems with her flight and wasn't able to make it.
Arecibo, I actually know that one from...
But certainly not least,
what was that
we welcome Dr. Javier Siemens, Principal Investigator and Co-Director of the NANOGrav Physics Frontier Center. And he's brought along with him a significant fraction of the NANOGrav collaboration. I think a rather boisterous faction of the collaboration also. Now for a brief introduction to the panelists who are representing the collaboration here today. From left to right on the stage, Dr. Stephen Taylor, Chair of the NANOGrav Collaboration, co-lead.
So it's not that I don't care about the panelists, I do, but their credentials are going to be lost on me. I am an average alien.
Cromarty, Chair of the Timing Working Group, co-author of the 15-year timing paper, and Einstein postdoctoral fellow from Cornell University. Dr. Michael Lamb,
really profound that
of the Noise Budget
Einstein
Group,
predicted the existence of gravitational waves, what, 70, 80 years ago, was it? Was it 100 years ago?
Dr. Luke Kelly,
and
Chair of the Astrophysics Working Group,
they're still proving his theories now.
Astrophysics paper, and an assistant adjunct professor.
That man had an amazing mind.
Berkeley. Welcome, panelists. Oh, I forgot one. Sorry about that. Finally, Dr. Maura McLaughlin, co-director of the NANOGrav Physics Frontiers Center.
Yeah, like how dare you forget Maura?
International Pulsar Timing Array and the Everly Distinguished Professor of Physics and Astronomy, West Virginia University. I saved the best for last, so it's okay. Okay. And now I'm pleased to introduce Dr. Sean Jones, Assistant Director for the Directorate of Mathematical and Physical Sciences. Sean?
Okay, here we go. The information that will drive all conspiracy theorists.
And I'm loving the energy that's here in the room.
6 years, I'm sure.
Good afternoon, everyone, and welcome. In 1995, the Hubble Space Telescope revealed the Hubble Deep Field, a tiny sliver of the night sky brimming with a veritable zoo of galaxies in various stages of evolution. In 2022, the James Webb Space Telescope refined and deepened that image, fantastically displaying galaxies more than 13 billion light years away from Earth. Aided by the state-of-the-art optical and infrared telescopes and decades of advancement in instrumentation and data processing, we perceive a static image of distant galaxies. Today's announcement shatters that perception of a static universe through the direct observation of gigantic gravitational waves washing across our Milky Way galaxy, spawned by cataclysmic events, including some from the most distant regions of the cosmos. These observations reveal a rolling, noisy universe alive with the cosmic symphony of gravitational waves.
Ooh, we got the computer-generated stuff now. That's cool. Okay, not quite as cool. I mean, the logo's cool, but I was hoping for actual... Oh, here we go. God, I love when they post these pictures.
Supermassive black holes lurk in the hearts of most galaxies, and galaxies grow by merging with other galaxies. When that happens, their black holes also merge and grow, becoming more and more massive over time. How exactly this happens is not fully understood, but the universe is telling us its secrets in gravitational whispers. We just have to listen. Just as sound waves are vibrations of air molecules, gravitational waves are vibrations in the fabric of space-time. When two massive black holes spiral toward each other, they produce gravitational waves that travel through the cosmos at the speed of light. If we imagine the universe as a grand symphony, these merging supermassive black holes are the bass players. As they orbit each other, these black holes play the deep bass notes that echo throughout the cosmic concert hall. But that's not all there is to the symphony. In the background is a faint but pervasive hum produced by the collective motion of massive objects throughout the universe. From the earliest moments of the Big Bang...
I cannot stress enough how much I appreciate that they are doing the For Dummies version of this whole thing to lead us all in here, because I need that.
NANOGrav is an NSF-funded collaboration of astronomers and astrophysicists. Our goal is to solve some of the deepest mysteries of the universe by studying the gravitational waves produced by these dancing monster black holes. These waves are light years long and can only be detected by the most extraordinary instruments. To measure these giant but subtle ripples in space-time, NANOGrav created a galaxy-sized detector using some of the most incredible objects in the cosmos, rapidly rotating neutron stars known as millisecond pulsars. Pulsars are the ultra-dense remnants left behind when massive stars reach the end of their lives and explode as supernovae. These pulsars are also cosmic beacons. They spin extraordinarily rapidly and with startling regularity, releasing pulses of radio waves with each rotation. Astronomers detect those pulses using giant radio telescopes. By monitoring the radio pulses from these ultra-precise cosmic clocks, NANOGrav can detect the slightest deviations in the regularity of their timekeeping, and these deviations trace ripples in space-time. This galactic-scale detector is called a pulsar timing array. NANOGrav has now observed an array of dozens of pulsars for more than 15 years, and the results are astounding. We are finally hearing the faint background hum likely coming from in-spiraling pairs of supermassive black holes. With time, astronomers expect to pick out the individual instruments in this cosmic symphony, revealing unique insights into the evolution of galaxies and the history of the cosmos.
Just, that's not my stream quality that's hitching there, it's theirs.
Excellent, excellent. Truly, truly amazing. Yeah, and great speaker as well. Yeah, and narrator. Truly, truly amazing. This achievement was made possible by an extraordinary collaboration involving more than 190 scientists from 70 institutions, the North American Nanohertz Observatory for Gravitational Waves, and NSF Physics Frontier Center. This project is a shining example of the transformative advances possible through long-term investment in NSF facilities and researchers and students at institutions ranging from small colleges to extremely large universities all across this great country. The National Science Foundation is proud to support daring team efforts like NANOGrav to expand our knowledge for the benefit of society. With us today are 5 members of the NANOGrav team who will describe their recent published results. We'll start with the chair of the NANOGrav collaboration, Dr. Stephen Taylor. Dr. Taylor?
Thank you, Sean. Distinguished colleagues, honored guests, and for all those following along at home, it's a pleasure and relief to finally share the following news with you. Over the last 15 years, we, the NANOGrav collaboration, have been on an audacious mission to find the low-pitch hum of gravitational waves coming from all over the universe, washing through our galaxy to stretch and squeeze space-time between the stars. Well, now we're here today to finally tell you all that patience is a virtue. Friends, our hard work has paid off, and we're really doing it. Even more excitingly, this is all the culmination of a coordinated process with our international colleagues using telescopes in Europe, India, Australia, and China. In the following, I'd like to tell you 3 things. First, about our detector, then about how gravitational waves imprint signals in our detector, and finally, how we found evidence for gravitational waves. First of all, we didn't do any of this just by building an instrument on Earth or even in the solar system. In fact, we harnessed a collection of astronomical objects in our neighborhood of the Milky Way to act as one big gravitational wave antenna. These objects are pulsars, and they're about as close as we can get to clocks in space. Pulsars are these super dense remnants of stars that have exhausted their fuel and contracted inwards, squeezing about the mass of the sun into the size of a city, and if you set that object spinning hundreds of times a second, blasting out beams of radio waves, you've got yourself a pulsar. Now, those radio beams I mentioned wash across Earth every time the pulsar spins around, and we measure this as regular pulses in our radio telescopes. In a way, these pulses are like the ticking of a clock out in space, and this makes pulsars perfect to study phenomena associated with Einstein's relativity theories. And while these pulsars are extraordinary objects in their own right, to us, they are the components of our vast galaxy-wide gravitational wave antenna. This is galaxy-scale hacking. Now, when gravitational waves cascade through the galaxy, they warp space-time between the pulsars, causing the ticking of these cosmic clocks to change in a predictable and correlated way among the numerous pulsars that we monitor. Without gravitational waves, the ticking rate of these pulsars should be completely independent, with zero correlation. Remember, these pulsars are separated by hundreds to thousands of light years, after all. But with gravitational waves warping space-time in the galaxy, and with Earth as the common endpoint of all of our pulsar observations, Einstein's theory of general relativity predicts a unique pattern for the correlation in those ticking rate changes between pulsars spread across the sky. Here is that pattern. This is the unique fingerprint of a background of gravitational waves, and there's nothing else we know of in the pulsars, in the intervening gas, or on Earth that can produce this pattern. Now, with almost 70 pulsars used in our gravitational wave search, this gave over 2,000 ways of pairing up the pulsars in a correlation analysis. For each pair, separated on the sky by a known angle, we measured the correlation of how much the ticking rate of their pulses are changing and offset from modeled behavior. And in what I show you next, we've distilled all that information into some average correlation measurements in 15 points between 0 and 180 degrees of pulsar sky angle separation. This makes it a ton easier to visualize, even though our detailed analyses don't require this. You know, I think I've dragged this out long enough, but that gives you a taste of what it's like to wait 15 years, okay? Here is what NANOGrav sees. Gorgeous. This pattern, imprinted in data from vastly separated pulsars across the galaxy,
I do respect a man who can look at a chart with statistical breakdowns on it and margins for error and say it's gorgeous. That is a special kind of human. I will acknowledge that.
Results without gravitational waves being present is less than 1 in 1,000, and in some of our tests, 1 in 10,000. That would be like trying to flip a coin and get heads 10 times in a row to 14 times in a row. And this significance will march higher in the future. NANOGrav is a gravitational wave detector and collaboration of people that intersects many different disciplines. My colleagues are next going to describe how we go from observing pulsars to modeling noise, finding evidence for gravitational waves, and ultimately constraining the astrophysics of supermassive black holes and theories of the early universe. It's my pleasure to hand over now to Dr. Thankful Cromarty to describe NANOGrav's pulsar timing campaign. Thank you.
So they're not dragging out their individual speeches either, which is good. That'll work.
Thank you so much, Steve. So, as Steve just mentioned, our detector isn't something that you could build in a lab or even launch into space. It's closer to the size of the galaxy, and it's made up of dozens of rapidly rotating neutron stars called millisecond pulsars. These objects are second only to black holes in density. They spin faster than your kitchen blender, and they have magnetic fields almost 1 billion times stronger than the Earth's. As a pulsar rotates hundreds of times a second, the radiation beam coming from its magnetic axis sweeps across our line of sight, giving the appearance of a pulsating star. Pulsars were first discovered in the late 1960s by Dr. Jocelyn Bell Burnell, and we are so honored to have Dr. Bell Burnell with us online. Thank you so much for joining. Their pulses arrive at such regular intervals that scientists initially joked the signal might be coming from aliens. In short, pulsars are unfathomably interesting cosmic clocks. We use a technique called pulsar timing to study them, which involves crafting a model that can predict the time of arrival of each and every pulse coming from a pulsar going far into the future. These timing models take into account every imaginable factor that impacts when pulses arrive at the Earth, from movement of solar system bodies to binary orbital motion, and even to the interstellar medium, which is the medium inhabiting the space between us and our pulsars. For gravitational wave experiments like NANOGrav, the precision of our pulsar timing has to be better than a microsecond. For some of our sources, we know when each pulse will arrive to a precision that rivals atomic clocks. Pulsars can be studied at a wide range of wavelengths, stretching from the least powerful radio waves, which are around the same frequency as your FM radio, to extremely high energy gamma rays. But their emission is strongest at low frequencies, and so we traditionally study them using radio telescopes. NANOGrav's been lucky enough to use some of the world's largest and most cutting-edge radio telescope facilities. These include the 100-meter Green Bank Telescope in West Virginia, the 300-meter Arecibo Telescope in Puerto Rico, and the 27, 25-meter dishes of the Very Large Array in New Mexico. So what's this detector actually made of, and what do our timing data even look like? The more pulsars scattered across the galaxy that we can time, the more sensitive to gravitational wave signals we become. And for that reason, NANOGrav's been feverishly adding pulsars.
Is it sad that my understanding of those radio telescopes comes entirely from the movie Contact? Because I'm pretty sure that's how I know why they all are where they are.
For 17 millisecond pulsars, timed using the Green Bank and Arecibo radio telescopes. The 9-year dataset had 37. The 11-year dataset had 45 pulsars. And the 12.5-year dataset had 47. Now today, we're sharing with you the NANOGrav 15-year dataset, which includes more than 15 years of timing for 68 millisecond pulsars. For the first time, we're also including data from the Very Large Array in our release. These data, as well as the brand new pipeline we've been working hard on, are available publicly starting today. Now, there's an enormous amount of science that we just sort of get for free from timing dozens of pulsars over a decade and a half with the world's best radio telescopes. With this much high-quality data, we've been able to do large-scale studies of our pulsars as astrophysical objects in their own right, instead of mere tools for gravitational wave detection. We can learn about their astrometry, which is a pulsar's motion through the Milky Way, probe the structure of the interstellar medium between the Earth and each pulsar. And for our pulsars that are in orbit with another star, we can sometimes measure the pulsar's mass and the mass of its companion using general relativistic effects. This last point is notable because precisely measuring pulsar masses helps us understand the fundamental nature of the extremely dense matter deep inside the cores of neutron stars. Now, I'll spare you from me droning on about how cool this is, but the takeaway is basically that once again, our astrophysical clocks can help us conduct science that just can't be done in an Earth-based lab. So the data in this release is the culmination of countless.
Honestly, I'm more excited or more interested almost to see how excited they are about presenting this information than what it means to my life, because, you know, at the end of the day, I'm still stuck here on Earth and working a job. But it is cool to see people advancing and being excited about new knowledge and new evidence.
Thanks to the hard work of so many people, we built our galaxy-sized gravitational wave antenna using almost 70 millisecond pulsars spread across the Milky Way, along with radio telescopes here on the Earth, and using well-tested techniques improved upon for decades. But even so, how do we know our detector is good enough to find the incredibly tiny signals produced by gravitational waves? Millisecond pulsars are the best astrophysical clocks we have, but they aren't perfect. At a very small level, they will wobble as they rotate, causing the ticks of our clock to arrive slightly early or a little late over time. Then, the pulses are delayed and distorted as they travel through thousands of light years of gas in the Milky Way. And finally, while we make the best measurements we can here on the Earth,
I have actually had nights where I feel like I have had thousands of light years of gas.
so we have to properly calibrate our data and clean out radio interference in our measurements. To make matters more difficult, each Earth-to-pulsar arm of our detector is unique. And unlike most detectors we build here on the Earth, we can't go to the pulsars to measure or tweak them. Our goal has been to extract the tiny signal from gravitational waves from many different sources of noise in our detector that mask that signal. It's a really challenging problem, as gravitational waves are constantly passing through our detector, and we can't turn the signal off in order to determine how our detector behaves on its own due to only noise. Many of these noise effects can be much stronger than the gravitational wave signal we're investigating, hundreds or even thousands of times stronger. Some of these effects change depending on the radio frequencies we observe at, whereas gravitational waves are the same strength regardless. So that's one of the many ways.
I also find it funny how, well, not funny, but the fact that they have to put simulated data up there is like, I think that that's something that most people, most scientists would say, oh yeah, they're just, they're putting something up that's very easy for people to see. But there is a cohort of people that would be watching this that are going to immediately take to Twitter and say, excuse me, that graph is actually not accurate because it doesn't have the appropriate X and Y axis labeled, and it doesn't match up with my own results that I did with my, DIY radio telescope dish that I made out of a dish TV receiver. So could you please correct it?
In each pulsar, the signal of a gravitational wave background may appear as a random oscillation over long timescales, but it imprints a unique pattern between pulsars that we can extract from noise. One of the benefits of our technique relies on the fact that our gravitational wave signal has a very special correlation when you analyze the data from different pulsars together. When the correlation between two pulsars is positive, that means the radio pulses are arriving either both early or both late. When the correlation is negative, then the radio pulses will arrive early in one and late in the other. Notice how Einstein's theory of general relativity predicts that the correlation in the time of arrival offsets starts positive when the pulsars are close to each other on the sky, becomes negative, close to 90-degree separation, then goes positive again when the pulsars are on opposite sides of the sky. Analyzing our 15-year data set, we find strong evidence of this correlation pattern, something like a 1 in 1,000 to 1 in 10,000 chance that the correlations would have been produced only from noise, depending on the analyses we perform. We find that these gravitational waves have an incredibly small strength, so small that they cause space-time to change by 1 part in a quadrillion. Next, Dr. Lou Kelly will talk about what sources will cause gravitational waves of these low frequencies and these tiny amplitudes.
Thank you so much, Michael. And as Michael pointed out, the amplitude of these signals is 1 part in a quadrillion. That's 1 part in 1,000,000 billion. This corresponds to a measurement precision of about 100 nanoseconds over the course of our 15 years of data. And now, while this has been an incredibly challenging signal to detect, it's actually booming loud in terms of gravitational waves. But because we're in the early days of measuring this signal, we can't yet confirm what sources are producing the gravitational waves. We believe, however, that they're produced by some of the most rare and most energetic objects in the universe, binary systems of 2 supermassive black holes, also the coolest objects in the universe. We know that these gigantic black holes lie at the centers of large galaxies distributed throughout the universe. While the black holes themselves are only as large in size as a solar system, they have masses as high as billions of suns. Now, as galaxies grow over cosmic time, they merge with other galaxies, and this provides the opportunity for 2 supermassive black holes to come together. For decades, astrophysicists have theorized that binary supermassive black hole systems could then form and produce exactly the types of gravitational wave signals that we're seeing.
I realize these are color enhanced to make sure that people can appreciate what the scientists are seeing in these images, but I never get tired of watching these images. Even when you see stuff like this, semi up close the way I have when I was traveling around in space, it's just nothing compares to the way people who have not been out there see things. And they're gorgeous photos.
Different tone of gravitational waves, which together produce a symphony or a hum that we call a background. Using new theoretical models, we have simulated billions of supermassive black hole binaries, predicted the gravitational waves that they would produce, and compared that to the signals that we're measuring. I want to share with you those results. Here, the vertical axis shows the amplitude of the signal corresponding to how many binaries are out there and how massive they are. The horizontal axis corresponds to the distribution of gravitational wave frequencies, how many binaries are emitting at different tones. Models appearing towards the right correspond to binaries evolving in isolation.
I like how they're keeping the actual plot off of the screen to build anticipation, and the difference between me and the average scientist is that I'm not appreciating any of that anticipation. I just want to see what it says.
That expects gravitational wave signals to show very little interactions, binaries evolving in isolation. In blue are new, more comprehensive models of binaries, starting when galaxies merge and evolving all the way down to the small separations at which those black holes can produce detectable gravitational waves. These models include interactions with the gas and stars and the nuclei of each of their host galaxies and produce much broader expectations. Finally, this is what we measure from the NANOGrav 15-year data. And if we zoom in, we can see that the data is consistent with both models. However, there is more overlap with the blue interacting simulations, hinting that perhaps binaries may not be evolving in isolation, and even in the strongly gravitational wave emitting regime are interacting. In either case, the signal that we're measuring is a bit louder than we expected, which means that supermassive black holes would need to form binaries relatively frequently and/or with quite high masses. We cannot yet confirm whether or not supermassive black hole binaries are producing the gravitational wave background. But if it is produced by binaries, then these models offer tantalizing hints about their properties. We'll need to keep taking data, continue to develop new.
Again, I have deep respect for anybody who can genuinely and earnestly be tantalized by data. That is a good quality in a human.
NANOGrav scientists who study the fundamental properties of the universe have shown that our measurements could also be consistent with signs of cosmic inflation, the rapid expansion of the universe soon after the Big Bang. They may even be signs of new, as yet undiscovered, fundamental physics. The way we'll be able to determine if these gravitational waves are coming from binaries or coming from new fundamental physics is by mapping where the gravitational waves are coming from. Just like we can create maps of the night sky using electromagnetic radiation, we can now create maps of the sky using gravitational waves. As our sensitivity continues to improve, we expect to be able to detect whether the gravitational wave background is stronger on one part of the sky than another, whether there are more instruments from one part of the sky or another. We believe that this would be a definitive indicator that supermassive black hole binaries produce the gravitational wave background. If it is binaries, then as our sensitivity continues to improve over the next few years, we'll be able to resolve the structure of that gravitational wave sky and eventually be able to detect individual binaries that are loud enough to resound above the background. This would be a particularly exciting opportunity for multi-messenger astrophysics, in which both gravitational waves and electromagnetic signals can be observed from the same sources. Once this happens and we're able to see and hear these sources at the same time, we would be able to make unprecedented measurements about supermassive black holes and answer fundamental questions about where they come from, how they evolve, and how they interact with the galaxies that they live in. Next, one of our great founders, Dr. Maura McLaughlin, will tell you more about our collaboration.
Not that I don't see the significance of deeper study on the black holes and these pulsars and all of that stuff, but I wonder if they can use this network to study things that are with the variety of things that they can study. If they involve finding other planets that can support life and stuff like that. I realize I'm probably talking about two things that are completely unrelated, but I can't help wondering about, I believe in science for pure scientific research, but I also like to know what the potential real-world applications of it are. Because that helps. It helps at least me get my head around it.
Was first proposed in the late 1970s. And worldwide, pulsar timing array collaborations started to form in the mid-2000s. NANOGrav started as a group of about a dozen scientists in 2007. We've now grown to 194 members, including 77 graduate students at over 80 institutions throughout the United States, Canada, and 12 other countries. We've also involved hundreds of undergraduate students and thousands of high school students in searching for pulsars, which directly increases our sensitivity to gravitational waves. And in fact, some of these students are watching right now from Pulsar Camp in Green Bank, West Virginia. So hey guys and girls. These results would not be possible without each and every one of our NANOGrav members. And I am personally so grateful to work with the most amazing and wonderful group of people in the world. We are very thankful for the US taxpayers who are watching this, as you ultimately support us through National Science Foundation funding. We got our start with an NSF award in 2010 from the Partnerships for International Research and Education program. And then we were thrilled to be named an NSF Physics Frontier Center in 2015. NSF funds 10 of these PFCs established to foster major breakthroughs at the intellectual frontiers of physics. And we are just so honored to be among this group. NANOGrav is also supported by the Moore Foundation and the Canadian NSERC and CFAR funding agencies. This result would, of course, also not be possible without NSF's significant investments in the Green Bank Telescope, the Arecibo Observatory, and the Very Large Array. The incredible staff at these observatories have worked tirelessly for decades to benefit not only our science case, but many, many others. Thank you. So what's next? Well, this is not at all the end of the story. This is just the end of the beginning. NANOGrav is already working on our next data set, which will have 17 to 18 years of pulsar timing data. And we expect that the evidence for the gravitational wave background that we have found in this data set to be much stronger in that one. And we're going to become even more sensitive with time as we increase the length of our data set, as we add more pulsars to our array, and most importantly, gain access to bigger and better new radio telescopes with more dedicated NANOGrav observing time. In addition, we are very proud to be a member of the International Pulsar Timing Array. The IPTA was formed 15 years ago and consists of pulsar timing array collaborations worldwide. Today, groups in Europe, Australia, India, and China have also released results from their most recent gravitational wave analyses. And we all see similar features in our independent data sets, which of course is reassuring and also incredibly exciting. Furthermore, through this collaboration, and partially supported through an NSF ExcelNet award, we are working with colleagues around the world to combine our current data set with pulsar timing data sets from large radio telescopes in Europe, India, South Africa, and Australia to form an uber data set that will be much more sensitive than any of the individual data sets alone. We aim to announce results.
Will an Uber data set be subject to surge charges if the radio telescopes are being used? I would like to know that.
This analysis will be truly transformative. It should result in a significant detection of this gravitational wave background hum. In this combined IPTA dataset, we may even detect our first individual supermassive black hole binary source, and likely also be able to observe it with electromagnetic telescopes at optical, X-ray, or other wavelengths, truly ringing in the era of multi-messenger nanohertz gravitational wave astronomy. Ultimately, we will produce an incredible map of invisible gravitational waves from gargantuan black holes spread across cosmic time. We will also probe some other exotic and less well understood sources for this background. We are so thrilled that you are joining us on this journey. Thank you. At one time, all we knew about the universe resulted from visible light, light we can see with our eyes. Then when radio and X-ray and gamma ray telescopes came online, we learned so much about the universe that we just couldn't have imagined before, like the radio pulsars that Jocelyn discovered over 50 years ago. Now, we can only dream about what we'll learn with observations in a different part of the gravitational wave spectrum from the LIGO detections that visionaries like Kip made possible, with continued investment in our science and in large radio telescopes. And we are certainly expecting the unexpected. All we have to do is keep listening. Thank you.
So the general mapping is the key thing, and it'll allow us to map more detailed. That's actually cool, because you can't know enough about the sky around you. Trust me. It's one of the reasons I ended up crash landed on this planet.
Let's see if I can avoid missing any more scripted lines here. So that concludes the presentation from the NANOGrav team. Thank you very much. Wonderful presentation. Before we begin our panel discussion, I'd like to address a question to Dr. Bell Burnell. Are you there, Jocelyn?
Yes, can I be heard?
Yes, we can hear you fine. So Jocelyn, when you discovered the first radio pulsars, did you realize how important
Oh, we are going to get so much feedback when she speaks.
in gravitational physics?
Well, we could see emitters had great potential because of their timing accuracy. But I guess we weren't thinking in terms of gravitational radiation back in the late 1960s.
I see. Thank you. I'd now like to welcome Professor Thorne to the stage, please. Kip, I will. Yep. Okay. The microphone's up here on the stage. Kip, of all the potential future NANOGrav observations, which type of phenomena is the one most interesting and exciting to you?
Well, I must say that the prospect of seeing can you hear me? Okay. The prospect of determining the properties of these supermassive black hole binaries, the largest, the heaviest black holes in the entire universe, is really exciting. But to me, there's something even more exciting that's on the horizon, perhaps for NANOGrav, very probably for gravitational wave astronomy generally in the decades to come. And that's to use gravitational waves to probe the birth of the universe. According to everything we know observationally and theoretically, the universe was born in a Big Bang singularity that was governed by the laws of quantum gravity, laws that are not well understood. And that singularity, however, had to give rise to gravitational waves. The laws of physics demand that that was the case. And whatever form of gravitational waves they gave rise to had to be amplified by the early inflationary expansion of the universe. And so those gravitational waves must carry a mixture of information about the birth of the universe itself, about the laws of quantum gravity that controlled the birth of the universe.
Here's where we get into the part that I truly, genuinely cannot understand.
Expansion of the universe, all involved together in a complicated way. So to me, the holy grail of this field in the long run is to explore the birth of the universe and extract that information that's carried by the gravitational waves.
I will admit that that is interesting to me, and I'm looking forward to seeing what sort of concrete information that can come out of this that is attainable to garden variety folks like myself. But yeah, I don't think I'm going to stay on for the panel discussion. I was looking forward to just watching this and seeing what they had to say, because I like when scientists get excited for good reasons. And even though it was very specific and focused around this one set of, what do they call them, pulsars, It was interesting to see. My prediction on Twitter was not accurate. I did understand more than 10% of it. I wouldn't go so high as to say more than 50%, but you know, it's always nice to expose yourself to stuff that seems interesting, even if it's outside your league. In any case, that's going to do it for me. I was just thinking that I would try this out and, you know, kind of, it's my first stream on this channel, and this seemed like a good thing to start with so that I could kind of see how things would go. Definitely planning on doing some more. Don't know when that's going to be. So the best thing, if you enjoyed my rambling, I do plan on doing things where I am actually more engaged and not just watching video. But in the meantime, feel free to drop me a follow if you liked what you saw, and the schedule page down below or my Twitter account is the best place to follow me if you excuse me, want to know what's going on and when I'm going live. That's the Twitter account. And for those of you who are hanging out there lurking, I really appreciate you being there, and I will hopefully see you soon.